Thanks so much for everyone coming here. I'm really excited to tell you a bit more about tabular foundation models. So what I want to do is go through a bit of the history, what we have done, why we have done these things, why we think this is important, and then show what our models are doing today. So I prepared a lot of slides, so I should probably start going through them. So first of all, right, what are we trying to do with tabular foundation models? We're trying to solve this age-old task of having data and assigning a prediction to these data points, right? So a classic example is this housing price prediction. You would have a table, you would have different parameters recorded about a house in this table and the prices, and then you want to learn how to make that prediction. And the most classic technique to do that we might have learned in school is linear regression. So just drawing a line basically through this multidimensional space of the parameters that describe your table. And this is the bread and butter of scientific discovery and also enterprise decision making. So a few more examples of what this would do, right? In credit risk assessments, for example, we're trying to predict from historical data if a business loan here, for example, would default or not. So we have different features recorded. We have the target, the default or not, and then for a new data point, we would like to make the prediction. The same for designing clinical trials, predicting if there's a responder or not based on biomarkers and whatnot. Same for churn prediction, predicting if a customer would drop out of or would leave the product that you've built. So all of these are classic data science tasks that, right, we have used linear regression, tree-based models, and this previous generation of models on for a long time. But we felt like there was a big opportunity to change this, right? And to make another step on top of this. My personal motivation for this was working with data in the UK Biobank. So this is this amazing study in the UK where for 500,000 people, basically everything was recorded about them. They joined that study, genetics were recorded, which diseases they would get over 15 years, different biomarkers were recorded, imaging, everything about these people. And now there have been over 18,000 studies looking at this data and finding out different patterns in this kind of data. There have been over 400 million invested into collecting this, and of course a lot of human time. And the problem was looking at this data, everyone built a new model. Every time you would fight the data again, right, you would maybe build a very simple model. So here one example is looking at something like the health risk based on the exercise volume, right? So you might use this linear regression, fit a straight line through this risk curve, and that maybe works reasonable. I mean, here we already see it doesn't really fit the data. But then the pattern is much more complex in the end. Maybe actually doing a lot of exercise can also be damaging again. And when people fit these very simple models, which are often the best thing that people can do, they miss the pattern in the data. And really, we are just scratching the surface of this incredible data that we have. So the question for me was like, what if we could build something that is maybe as smart, understands the data as deep as ChatGPT understands language nowadays? Why don't we have this for tabular data? Yeah, and this problem was even more obvious working with genetic data. They are really, right, for the biomarkers, we could build a tree-based model. But for genetic data, what we were doing when we were predicting risk of a person based on their genetics, it's basically just doing association and then correcting that a bit for the genetic structure that occurs in the population. But it's a very simple algorithm and there's no interaction between different genetic positions. So these are extremely simple models. And of course, then we can't really find out what is going on. So there was a point I made a moment ago, right? Foundation models, they have really transformed every other modality. They've transformed images, they've transformed voice, they've transformed videos, they have, of course, transformed language. They made the results that we can get much better, and they democratized access, right? A couple years ago, a few thousand people probably used language models, and now it's everyone. And we believe we could have the same thing happen to tabular data. And in fact, the space is undergoing a similar revolution. Now we are building, and there's a lot of companies nowadays that are building tabular foundation models. So if we look at the leaderboards, like this one on Tabular, which measures the performance of different deep learning algorithms on a large set of representative tabular datasets, all the best methods are methods that were developed in the last year or last year and a half. And this is actually a snapshot that is like 2 months old. By now, we created another model that's actually another big step change. So finally, the space is again moving. Right before, the methods that are kind of on the left side of this red box, those were developed 20 years ago or maybe 10 years ago, and there were only slight improvements to them. So there wasn't really a big gradient change in the way that we could model tabular data, and this has now completely exploded. And these benchmarks, they also transfer to real-world data sets. Right? So our model has millions of downloads. There's thousands of use cases out there, and some of the ones that I think are really, really interesting are, for example, a team that did a pancreatic cancer test using our models in Nature Communications. Companies like Tactile in Berlin that are doing financial risk modeling are using these models. It's being used for car making decisions in car engineering and thousands of other use cases. And now also at ICML, for example, in Korea, we will have there will be a workshop on structured foundation models. And there were like over 200 submissions to that workshop, so the field is completely exploding. Yeah. There have been these LLM companies, of course, right, building models for unstructured data, kind of in any domain, like OpenAI, Mistral, Anthropic. And now we are introducing this new class of tabular foundation models where we are driving the change there, that are making predictions and really learning deeply to understand databases, CSVs, spreadsheets, and time series. And they make predictions on this data and help you understand the statistics and patterns in this data. An intuition for why this would be working much better, and this drove why we built this, is that in traditional machine learning, you start every problem from scratch. You have dataset A, maybe an EHR dataset with health records. You build a model, you get predictions, and then you get a second task. It's a CRM task. You build another model. There's no transfer between them, right? We've built there was a paper maybe written, there's an architecture, but model A learns nothing from model B. That is even more of a problem if you think also about maintaining these models, right? You're also doing the data cleaning, feature engineering. You have to deploy the models. You have to keep them in production. You have to govern them. And this process is also the same every time for every model. And you have to keep these many, many models running at the same time. So we need months to create solutions to problems. Often, I mean, it depends on the quality that you want to get. There's no knowledge transfer, and there's also a lot of engineering time spent on maintenance. With a foundation model, we have this one single model that can learn now across data sets, that can transfer patterns between them, right? That is the magic of ChatGPT. It has seen data from a completely different domain, and it can take that into the domain that you care about. And that is the way that our models work as well. And they are just accessible through an API or through our open source package. So it's always the same workflow. You don't have to really think about how to optimize this. Maybe an intern, right, built the data pipeline some time ago, and now you are kind of left to keep it running. It's always the same approach, and that makes things much simpler as well. So a question that we get a lot is, why don't we just use LLMs out of the box, right? There's kind of this feeling that AI are LLMs and they should be able to do anything. I think like people in the image domain probably don't get the same question, and that's kind of what I want to use as a reference, right? You also wouldn't take your image, put the pixels into text, put this kind of RGB string into your model and expect a language model to be good at that task. And it's very similar for tabular data. Tabular data behaves very differently to text data. It has this two-dimensional structure, or if you have a database, it's kind of a multi-dimensional structure where certain things interact in a specific way. Then numbers are very important in tabular data, and there's these famous examples of LLMs being terrible at numbers, right? In the left-hand side, kind of like not being able to do simple arithmetic, right? The second one is just flattening that leads to a lot of inefficiency. Um, then LLMs are really big. The parameter counts per embedding within an LLM are very large. So a table is often in the billions of tokens. If you think about what the best language models now do, they have maybe a million tokens, and a table is just much larger usually. So you have to also scale down the model. And then LLMs are non-deterministic, right? You put in the same thing, you get a different result every time, and they hallucinate. So all of these things are solved with tabular foundation models. They are built specifically to tackle all the things that really matter when we do prediction on tables. Yeah, and to build this, we've built a world-class team. We're based here in Berlin, in Freiburg, and in New York. With Frank Kutter, who has been in the field for a long time, researching automated machine learning and deep learning. Me and Soraj as the founders. And then we have people like Jan LeCun and Bernard Schildkopf on our scientific advisory board, helping us kind of go beyond LLMs, right? So this was now the motivation for why tabular foundation models should work, right? Why that's important and where it matters. And now I want to go through the different works that we have done. So 2022, we built the first version of TabPFN. Not going to go much deeper into this because it's a long time ago. And then in 2025, we published our first version of TabPFN in Nature. And this was really the first time that we showed like this is not only a proof of concept, this is something that you can use. So this was the most cited AI paper that year. Yeah, we immediately saw a lot of traction from this. So a big problem in building foundation models is, right, getting the data that you use for pre-training. In language modeling and image modeling, I think that was more trivial. All this data is on the internet, at least if you kind of just take it, as maybe other companies have done. For tabular data, this data just is nowhere to find. It lives within the enterprises, it lives within the companies. So if you took the kind of publicly available data sets, you just wouldn't have enough to build a foundation model. And I think this is a big part of why this wasn't really done before. So how do we bridge that gap? We looked at learning algorithms with our models, and this was basically the foundation for building synthetic data that would go into training our models. So our models are really trained purely on synthetic data now, and the intuition for why we thought this would work was that we had a work where we learned, for example, to do logistic regression, the simple technique that we looked at in the beginning, but just showing our model a lot of different examples of how logistic regression would be solved, right? And then we went to the next algorithm, like Gaussian processes, tree-based approaches, and we saw that the transformers, they could learn to approximate this algorithm, and they could do it in a Bayesian way. So they would model the uncertainty that you would have about the underlying parameters of these models, and so of the logistic regression, and they would give you a prediction trying to mimic it, but uncertainty aware. So we thought, right, those are the best methods that exist right now. And this seems to be something that we can extend now to go into synthetic data and make this much better, right? So whenever we saw a challenge that tabular data had, like missing values, like outliers and these things, we would just put that into the synthetic data generation and make the synthetic data generator better and better and better and train our models on this. So the conceptual step maybe that we took away from just the pure classic algorithms was as well that we thought about principles of causality being part of the synthetic data sets. So in a causal graph, you connect the nodes of the network, and these nodes would then represent features in the data set. You would connect them through some function. So each of these edges in the graph, each arrow is a function in it. And then you can think about each function again being one of these models that we've seen before. So for example, being in logistic regression, being itself a tree-based model. So you can mix different synthetic modeling approaches and previous algorithms into this graph. And the graph would then reflect a data set. So if we're generating synthetic data sets, we generate for each data set such a computational graph with these edges, we pick different positions in the graph that are going to be the features and labels of the resulting data set. We assign some values to it or functions. So those are pretty simple values right now. And then we sample noise that we would propagate through the dataset for each row that we want to generate for this dataset. We take a different initialization of this graph and we pass this initialization through the graph. We read off the features and the labels, and we would here, for example, have these 3 different rows of our dataset. If it's classification, we just take the outputs and we apply some kind of discretization to the output as well. And then we get the resulting synthetic dataset. Then another principle that we built into it was principle of simplicity. So we would make sure that most of the datasets that were being generated are relatively simple, so that the algorithm also learns this simplicity principle. Potentially, that's actually not necessary because there's this Bayesian perspective that with a parameter uncertainty, things actually collapse to simple things. But we made sure that it would be really going for simple explanations. And then if we look at the full picture, the full synthetic data generation recipe, basically, right, we sample hyperparameters for the graph generation. We sample the computational graph. We then sample these computational edges in the graph. We generate the dataset, read off the data, and then we do some post-processing like adding outliers, missing values, and anything that we see being relevant in real-world tabular data, we add to the synthetic data generator, and we learn with our models to solve the task that we show it, right? So those are just some more graph of how the data could look like, right? The computational graphs here on the top, they're much more complicated, and then the functions are basically on the bottom here. And on the right-hand side, you see some of the generated data sets. So everyone who has maybe looked at tabular data before would agree these look quite realistic. And then the model architecture, right, is the second part. So I said before that language models, they just aren't built to handle tabular data, right? So we thought about what is the way to build an architecture that handles tabular data. Our models, they take as an input an entire tabular data set. They take the training data and they take the test data as well, just without the labels of those test data points. And then they return something of the shape of the test data points, so that this is basically the entire learning algorithm implemented in the forward pass of the transformer. So it takes an entire training data set and what you care about as an input. This data then goes through this 2-dimensional transformer, so a transformer that looks at the rows and columns in separation, and then there's mixing over these different layers over 12 different layers that were repeated in this model version back then. And then as an output, we get this probability distribution. So this is something that can also specify the uncertainty of the prediction that we're making. The model would learn that Gaussian shapes, right, are very common, and it would learn that they are not that they're the right solution if you want to be uncertainty aware. And if there is evidence, right, for more complex output distribution, they give you that more complex output distribution. So we have on the left-hand side here the pre-training phase where our many synthetic tasks go into. The synthetic tasks, right, go into the architecture that we just saw, and our model is trained to solve each task, each data set in the right way. And if we do that for hundreds of millions of data sets, then we get a pre-trained model, and this pre-trained model can then be used without any further training. Now you just pass in the data set that you care about. It's a bit like with a language model, the context for our models is now the data set versus kind of the text that you would give to a language model. And our model then gives you back the predictions on the missing values that were in the data set. And there is this synthetic to real transfer, and right, we see that this works exceptionally well. It's maybe the intuition is again, right, we are learning these learning algorithms. We're learning things like a more complex linear regression, and that worked in the first place as well. So you didn't really need to have the most realistic data. You just have to have data that shows the right algorithm to solve a problem. If we look at the output distributions of our models. I think this is kind of a nice, like, classic sklearn plot. You see that our model on the right-hand side has these smooth decision bounds. It really learns to calibrate its uncertainty. Compared to, for example, the decision trees, right, that at least in a simple form give you these very rugged decision and uncertainty plots. They have these discrete bounds, and that is, of course, something that we wouldn't expect to be the right solution here. Looking a bit more into the uncertainty quantification of the models, right? I think this is something really interesting and new that the models can do. They give you right away a probability distribution over the output space, right? So they don't tell you just this is the house price that I expect, but this is the probability that the house price falls within each tiny bucket of the output space. And one example that we thought would be great to show this is the photon double slit experiment. So this is like this physics high school experiment where, photons, they are inherently probabilistic, and the interference patterns are kind of creating this complex output distribution on a screen. And TabPFN could mimic even these like five modal peaks very well, and just do that in a single forward pass.
Right.
And then foundation models, deep learning models, they also have a way to be fine-tuned, right? This is something that we saw a lot with language models happening, maybe a bit less popular now nowadays, but we can do the same thing with tabular foundation models. We can fine-tune them for one specific data set, or we can fine-tune them for domain of data sets. So maybe if we have these biomarker data sets, we have hundreds of them, and then we want to learn to be better on this entire class of data sets by fine-tuning on them. We can also use the models and the uncertainty quantification to do things like data density estimation or outlier detection. We can generate synthetic data by using them in an autoregressive way, and they also have embeddings that you could use and extract for a different task that you would get in a single shot of the model. So this was TabPFN version 2. Then in November last year, we had version 2.5. It is what you would expect. It does better on the leaderboards. It also scales further. So we had a 10x scaling of the dataset shapes that could fit into the model. So this is the big kind of limitation that we're always fighting, that the models can take small data sets still relatively. Right, in language models, you have this 1 million token context. For us, we are now going to tens and hundreds of millions. But anyways, a table can be trillions, and this is kind of the frontier that we're always fighting. So 2.5 took the dataset shapes further. It was better on the dataset shapes that you had seen before. We also built in a distillation engine, so something that can create a simple tree ensemble, an MLP, a linear regression, but that was informed by our model and that would be more accurate on the same data, but that would still fit into kind of like the old workflows, right? Because we're thinking about how do we get this as fast as possible into the old kind of machine learning workflows, and the simplest way is just create the same thing again. And so we can basically create any output that you would like for this problem. And then we also introduced scaling mode, which is something that works around our native model. It's a bit like RAG in language modeling again, something that retrieves the relevant context for the problem, and in this way allows you to take in a much, much larger data set, even though the native model doesn't see the entire context. And then in May, so just a bit over a month ago, we released TabPFN version 3. Same thing again, we scale 10 times larger, so this is a pattern, I think, and we expect this to be the same again at the end of the year. So now we had 1 million data points natively, and then we have the scaling mode on top of this again, right? So we can take this to up to 1 billion data points. And then we had, of course, another improvement in the predictive accuracy, quite a big step. And then this is maybe a bit less expected. We also introduced thinking mode, which is something that can take more time on a problem if you care about taking more time, if you care about spending more computation on that problem. And that again completely exploded the performance of our models, right? So I think this jump just takes it into a different league here on the benchmarks. We also looked at kind of going beyond this IID setting, right? So I said before that any kind of thing that we saw in real world data, we would put into the synthetic data generator. And right, XGBoost, linear regression, and so on, they were really preoccupied with solving the standard IID prediction task. So the kind of easiest table that you could get where you expect the data to be well behaved. Real-world data doesn't do that usually, right? It evolves over time. You have these groups within datasets. You have special data types mixed into your tabular dataset. And now with the foundation model, we can look at these new problems and these new kind of out of these unexpected data distributions, and we again put them into the synthetic data generator, and we get better at this. So this is, I think, going to be the new frontier, thinking about, well, what would you like to do with a tabular data model, and not what could you do in the past. So one of these things is text data and working on data sets that have columns or cells that encode text themselves. Here we are doing much better than previous approaches. Another one is looking at many class predictions. So if you have hundreds of classes, this was kind of a limitation that previous models had, and something that we built into our models. Then having many features, so often, especially medical data, right? The genetic data set is one example where we have a lot of features, maybe millions. So we're looking at getting better at these very wide data sets. And then this quantile regression, so predicting again the uncertainty. Forecasting with our models, so using our models to not do the kind of interpolation task within a data set, but taking a time series and forecasting that, right? So there's, for example, Chronos 2 that did really well recently. So we are next to Chronos 2, the next best model on these multivariate time series tasks, even though our models are not really time series models, but it's a table as well. And then things like relational data, this is also something that's very important to us, right? You want to be able to take your entire database as a context and not just a single table. And here we showed that just taking relatively simple wrappers around our models can already do this. And we are working on the more native variant of this as well. Another one, and this one looks very simple, is kind of extrapolating trends, right? If you think about the housing data set again, maybe you get a house now that is 10 times larger than any that you would have seen before. Now, a tree-based model basically cuts off at the end of that distribution, and really any model has problems going out of distribution and even extrapolating these very simple trends, right? So even just having a straight line, of course, a linear model is great at that because it's kind of exactly what it would expect. Tree-based model would just cut it off. In MLP, you really just don't know what it will do. And really, there's no model class that is good at extrapolating these different trends that you could see beyond the distribution that you had in your training data. And TabPFN 3 was now trained to be specifically good on out-of-distribution data. Of course, it's a bit hard to know what to really do there. There comes into play again this learning from other real-world data sets, learning and having the expectation of these causal models and relatively simple, well-behaved functions, and expecting that that trend would then continue beyond the distribution. And you see that for these intuitive examples, right, it gets that right. And this is, yeah, I think something that is going to be very important, right? Because usually we care about doing predictions on a new part of data. Trustworthiness is something that we think about a lot, right? Having this new model class, we have to find a way to show people that these models are well behaved. We already spoke about the uncertainty prediction, right? If you see a tree-based model just having these weird artifacts, you probably wouldn't trust this. Our models are much more behaved out of distribution again. tree ensembles, right? They are often, people say those are interpretable because you have this decision tree, but then the really good models, they average hundreds of these trees into an ensemble, and of course that isn't interpretable again. And then if we look at post hoc techniques of looking at a model like SHAP analysis, this is something that we apply to our model as well. And we see again the smoothness leads also to more interpretable SHAP values. So you would expect your kind of your feature attribution not to jump around with every data point. And this is something that we see from our models. If you want a tree, right, we can give you a tree as well through this distillation kind of approaches. Or we can also think about other more interpretable model classes like general additive models, these GAMs, or symbolic regression and learning these interpretable output distributions. Also, TabPFN has almost no hyperparameters, right? The hyperparameters that we have are kind of the computational effort that you want to put into it. The other hyperparameters, we would just say, don't tune these. And that means that if you do an analysis with different people, you get the same result. That you don't just tweak a parameter and suddenly your model says something completely different, or that the feature attribution suddenly changes with a different regularization parameter, right? You maybe understand something about how the specific model behaves, but not about how it should behave or how the data really works. And with a foundation model, you take these kind of noise and these confounders out of your analysis. Then we also looked and did some research. So this is what went into our output out of distribution models. We made them better at out of distribution data. This was a NeurIPS paper that we then integrated into our models. And then you can also use our models in, for example, double ML workflows. The models integrated into the double ML library, for example, and you can use it there again in causality and doing this what if analysis. It is a big problem if changing a hyperparameter changes something about the what if analysis. So having here in these complex models that taking out this confounder of hyperparameters is something that we believe is quite important. So what's next? I think I already teased some of that. The relational models, of course, going larger, being faster, being more robust in inference. And then one project that we are especially excited about is interventional predictions, right? So with double machine learning, we are predicting through some kind of controlled experimental setup what would be the prediction of a data point. But I already said before, right, our synthetic data generators, they are based on structural causal models. So these causal relationships that we would expect in data. And now we are looking at learning with our models to directly predict the causal effects that you would have in a graph. So not only taking that to make a prediction that is kind of most likely to occur, but also training our model now to predict what happens if you intervene on the system. And this is again something that we can simulate in the data and then train our models to do. And this is, I think, right, the kind of holy grail of data science to some extent, because usually we care about understanding how we can intervene on a system and not just saying what is most likely to occur. We care about changing something about the world. Our kind of preliminary results, so this again a NeurIPS paper from last year, show that this is quite successful. There are also now a couple of approaches working in this field, and we want to build a new version that is making it much easier, right? Because causal prediction is, you almost need a PhD, I mean, or at least a lot of experience to do this well. And we want to also make this field easier for people to approach by having a foundation model where you put in your data and it can tell you something about the what-if relationships in it. Model deployment, right? So we have different case studies, for example, working with Hitachi on anomaly detection. We are working with TD on treasury forecasting. We're working with Credit Plus on credit risk assessment. And we have these different model deployment modes, right? We have an enterprise mode, we have an open source mode. So our models are available on GitHub. You can try them out. You can use them for research. If you want to use them for commercial reason, you speak to us about that commercial access. And then we also have these improved models like the thinking modes, like handling text data and so on in our enterprise features and on the API. So the API is the place that is this is the middle part here, right? That is the easiest place to use. You don't have to think about the infrastructure anymore, hosting a GPU and so on. It is kind of the simplicity that you have of a language model where you have an API, send your prompt there and get a result back without having to worry about the infrastructure. Right, the Python package, we have that also for commercial use until version 2. And then we have this managed deployment, which is if you don't want to go through the API, but you have a commercial use case for this. And we do this then in a like VPC on-premise, work with, for example, AWS, Azure, GCP, and so on to have a safe place for the model to live and know that data transfer out of that infrastructure. And then this is the last part, right? So what we think is going to happen as well, right, is that agents will drive more and more of the decision making. And we want to give with our models the agents a way to kind of ground the decision making in actual data that was observed, right? So the great thing of it about a tabular foundation model here is that it can be jointly optimized with an agent, with an LLM, and that it is very fast in prediction. I think that's something that I actually didn't mention, right? The forward pass of a transformer takes seconds to train, so you don't really have a training phase anymore, and that works well in an agentic setup where the agent doesn't want to wait right for a result. It just goes back and forth with the prediction that you have and the data and the context that you have. So we're building our models to be better together with LLMs and agents. And then you can do things like ask Anthropic's model if you connect our MCP to make a prediction on your data, and without connecting that MCP, right, it will just decide kind of based on the randomness that a language model has. It would decide on the learning algorithm, maybe chooses a logistic regression or something really bad here. It shows something pretty bad, and with our model, it just has a right API to do prediction on that data and work very fast. Then we have this also integrated, for example, in Databricks, so you can enrich these dashboards. And we have also this playground where you can just upload a data set and you get a prediction back in seconds. We're always looking for outstanding people. We are hiring in Freiburg and Berlin, so we're based in these two places and New York. Thanks a lot for the attention, and here's a few relevant links. Happy to take any questions. Thank you.
Yeah, thank you very much, Noah, for this very nice talk. So when I asked Noah how many minutes questions he wanted, he said 10. So there must be a lot of questions. Yeah, please start in the very back, please.
Yeah. Well, hear me?
Yeah, well.
Yep.
I mean, in your training data, you don't see as a story. The data of your problems.
It seems, as you explained, but you're using synthetic data, different from a LLM, which had a host of real-world data in it. So I would actually expect that such a model performs not in the same way as a real-world engineer who knows the mathematics or the natural science or the financial science relationships of a model. Are you trying to be better than human engineers, or is your use case rather to give a first good shot and to save engineering time for this first shot?
Yeah, that's a very good question. So that idea of our model is having a better tool for the data scientists to work at, right? At the moment, a data scientist interacts with an XGBoost, a tree-based model, linear regression, does feature engineering around that and prepares the context around that predictive model. And prepares it in a way that the model picks up on the most relevant pieces and that the model does the best prediction, right? And this is the same thing that we do with our models. You bring in the context that you have about the problem by enriching the data set, by maybe showing some of the most relevant and complex interactions in the data set to the model. And if you show it a lot of different interactions, the model is now very good at kind of ignoring what maybe wasn't the right hypothesis and what was the right hypothesis. But it is really a statistical tool to help the data scientists bring in the real-world knowledge that they have, but then not have to worry at the same time about kind of which parameter did I choose in my tree-based model, and was that maybe the reason why this feature wasn't correctly and this context wasn't correctly picked up, right? We're taking this part out of the context engineering. If we go a bit forward, we want to also include more and more of the real-world context into our models, and there would, of course, then be a language model or some kind of real-world trained context becoming into play. So we're thinking about how to merge these pieces more closely together. But it is on the synthetic data. It's really a statistical tool that has seen a lot of statistics and helps you do that. Does that answer?
Yeah, partially. I think there's many more questions than just me.
Okay. Yeah, I think maybe over here first. Yeah, sure.
Thank you for the talk first. I'm interested you had a slide on thinking, but I felt like you quickly glanced over it, and I don't fully understand how the model architecture that you showed can perform something similar to the thinking that we see in LLMs now.
Yeah, I mean, that's an excellent question. Unfortunately, not one that I can really answer. So this is one of the things that we are now building up within the company also. So yeah, something that I can't really answer right now. Maybe in a half a year or a year, we're gonna write a bit more about that and share a bit more about that. But at the moment, that's proprietary.
All right, thank you.
Maybe over there.
As you mentioned, that it is trained on synthetic data. I wonder if you have tasks that require looking at huge amounts of historical data and some very special patterns in it. Would it be able? I mean, how would it work in practice? Would it by a rack or something select some data and get the proper result then, or what would it do then?
If you train the language model to do that, or sorry,
if your your model,
if we trained it on real world data instead of synthetic data, basically.
Yeah.
I think it depends a bit on like the parameter size that you would have and how much data you would have in the end. I think like these models are really small, so even if we had a lot of real world data at the moment as they're built right now, they couldn't encode the knowledge of the world in it just because they are so small. I think they would still continue picking up kind of an algorithm within the data and kind of what commonly solves the real world data that you've seen. There would maybe then, well, I think like there would be common feature types maybe picked up, maybe things like embeddings or something like that always have a certain behavior and are often in this real world data. It would learn to pick this up again and just it's very hard for me to predict what would happen in the small form, right? It learns to continue learning this algorithm. If we scaled up the model as well, and then we had really infinite data, I think then we would have this combination of a language model and a statistical prediction machine. And what we would then, I think, see is really something that can think about, what in biology is the most likely association between two genes, for example, puts that together while thinking about the statistical pattern and the association between two different features in your data set, and kind of the loop that we are now taking, going back and forth with the statistical model and our real world context, right? The data scientist doing that. I think that would just happen at the same time. And yeah, I mean, we would just be much better at prediction, I think.
How many trainable parameters do you have?
That varies a bit. The smallest one had around 5 million, and now we are, I think, at 40 million again. So,
Thank you.
Yeah.
Thank you. Thanks for the talk. I wanted to ask, because a lot of tabular data sets in the business world need to deal with some bias in the data. Does this model in any way can handle bias, or is there anything we can set up for it?
Yeah, so these biases are, if I understand correctly, kind of things that we know the model shouldn't consider, right? So something like a discriminatory feature or something like that. So we have two ways to look at that. We had a publication also at NeurIPS on learning fairness. TabPFN is what it was called. It's a model that takes away in the causal graph these unfair edges and removes them kind of within the model itself. That, I think, is kind of like the way that, to me, there's counterfactual fairness. So counterfactual imagining the world without that connection would be the best way to do it. But it is, I would say, kind of hard to explain, and it's kind of hard to prove that it is actually doing that in the end. So I think this is actually still a bit of an open research field. There is these kind of post hoc approaches, right? And this is what you can do with other model types as well, where you go and you look at the distribution that the model predicts, and then you correct that distribution afterwards. And our model can be connected with these popular post hoc techniques as well. And this would be, I think, the practical approach to do it right now. It's a bit less like intellectually satisfying, but there is certainly ways to do that aren't very hard to do as well. Maybe we can, I don't think we have an example in the repository, but that would be something great to add, actually.
Thanks very much. What I find really fascinating is that your model seems to generalize over very different data sets. So I'm wondering, is it just so many data sets that you've used for training, or is there some universal principles across the data sets, or what is it actually that makes it generalize so well?
Yeah, I think the intuition coming from the learning algorithms is actually the one that maybe makes this makes it for me the clearest, right? So if you think about a linear regression, the linear regression kind of, it doesn't really reflect the real world. It's not realistic, and the data that you would generate from a linear regression model isn't reflective of the real world. But still, it solves tasks really well, because there is some principle of the real world of kind of connections between variables being relatively simple and so on. I think this is the same, this would be for me the most likely explanation for why it works so well. I think there is actually relatively simple statistical patterns in the world that we can transfer, things like Gaussian distributions being more likely and so on. This is kind of what the model learns. It is a statistician on steroids, I would say, but it is really putting together a lot of statistical concepts.
Thanks.
Yeah, maybe.
Yeah, thank you for your talk. Very interesting. I come from an R&D production environment, so we have a lot of KPIs that depend on hundreds of parameters, all convoluted. So this is exactly the kind of problem that we're facing and that we could solve through this. And I wanted to pick up on the first question and what you just mentioned, that you put in synthetic data that is somehow correlated to business logic, physics, and so on. So does the model at some point, like LLMs, develop a feeling of what real-world applications would look like? Sort of like a physics-informed model without actually having input any formulas, but just knowing, as you said, data points are typically contiguous, behaving according to certain functions, etc. Is this emerging?
Yeah, so in the kind of computational edges, we actually put in a lot of kind of formulas, physical and behavior, spatial, like structures, rotations, and all of these things. So in the pre-training phase, it sees a lot of this reward behavior, and I don't know if I know a pattern that looked specifically at kind of physical data and how much it matches that, right? There's also these physics informed data sets, but we had, for example, a plot in the version 2 paper that showed that like these sinus curves with a slope and all of these things, they are learned pretty well with a very little data. So if we think that those are more common in physical data, I would say yes. Is that what you're thinking of, or?
Yeah, basically our world is controlled by a small set of pretty generalizable functions.
Yeah.
They're all convoluted. So if the model is able to learn that, it would be very helpful.
Yeah, I think that there's really some of the kind of general patterns that it learns. Yeah.
Hi, I also wanted to thank you for the talk, and I'm a bit curious, like, could you explain us a bit how actually the model sees time series as tables? Because usually LLMs are very bad with time series, and I thought it was because of the nature of the attention mechanisms. Could you tell us a little bit?
Yeah, I unfortunately I think I don't have the slide here, but if you think about interpolation being the task of filling in maybe a certain column or this column for certain fields, the time series prediction task would be kind of extending the table at the bottom and kind of like taking the next values. What we do with our models is we take a time step and then we create these auxiliary features for the time step, like the date, the day, frequency data. So a bit like SK forecast. We also integrated an SK forecast, and then it takes the data point that was observed for that, and then for the new date that we care about, we again generate the same auxiliary features and give you the prediction for that. Again, we are looking then for the kind of underlying patterns. There's probably some sinus, some seasonal patterns in there. And since the models learn that easily, that works well. The model has this kind of full view on the data set. So the popular time series models, I think they have this causal attention. It just runs forward and doesn't also run backward. Our model actually kind of like sees everything at the same time. Yeah, I think is an advantage actually for the model. But it takes a bit more computation, and maybe we'll also build a model that is specifically built for that as well. But in SK forecast, if you're using that, you could just try it out and try TabPFN in there.
Cool, thank you.
Thank you for introducing the foundation models for tables. So my question is more in terms of how a user would use it. And I'm just wondering, by prompting or what ways currently in the model's implementation are available for a user to influence the causal graph that the model would build? Is it totally automated, or can model prompt in some reasoning to the model, or maybe add additional row which gives some kind of language reasoning information to the model to influence the causal graph that it will build and do it?
Yeah, we are actually working on integrating a way to, or like adding a way to add the causal graph and add language to the model as well. At the moment, it is through the feature engineering. So if you think that there is this right connection in the data, you create a feature for that, you add it. I think this is really where we want to go, through language or causal graph. Yeah.
Thanks.
Okay, so maybe one last question, because then we need to find someone
Hi, thanks a lot for the great talk. I really enjoyed it. I have one question for regarding the data generation. You said that you use these generative causal models for generation and then add errors and anomalies on top, like as a posteriori step. Could you elaborate on this? Because I think, I mean, like there's an incredibly complex I don't know, like area, what kind of errors like there is in data, like outliers, I don't know, distributional errors, frequency errors, something like that. And I think it probably influences quite a lot the expressivity of the generated data. Could you elaborate how you tackle these problems?
Yeah, that's a really good point, and there's probably a lot that we can do better in the synthetic data generation to have a model for each of these things, right? Each of these errors. At the moment, we have two kinds of errors or missingness. For example, ones that just come post hoc, just come on top at the end of generation, and then we also do that a bit while generating the data, or we at least do it using a pattern that is associated somehow to the data, so that there's basically the two concepts like missing at random or missing not at random. But I think there is a lot to be improved there. Be super interested to hear more if you have some thoughts. But at the moment, right, there is errors that have no influence, that just come at the end, and some that also mean something for the model.
All right, thanks.